Welcome students. Now in this module we are just going to learn something more about hypersonic regime, which you have been already doing in the last and the previous few of the video lectures. In this module we'll do little different from what we have been doing till now. We have been actually looking into the historical facts as well as the evolution of the shape and the hypersonic philosophy. So it was more of a story kind of thing, but now we are just entering into the technical mode. We look into the technical aspects of the hypersonics, but still we'll try to avoid the equations. So still it is a theory, but it is more of a technical things which we are going to look into. What is hypersonic, and can we define the hypersonic the way we do to supersonic and subsonic? We all know that supersonic and subsonic is defined based upon the Mach number, and there is a very sharp boundary across which supersonic and subsonic are differentiated. So if the Mach number is less than 1, we call it subsonic. If it is more than 1, we call it supersonic. In between there are some a thin boundary, a thin range is there. Normally we take it as Mach number 0.8 to 1.2. We call it transition, in which the flow over any body normally has a mixture of characteristic of subsonic as well as supersonic, and but any Mach number more than 1 or less than 1 are simply differentiated as supersonic and subsonic kind of thing. We don't define hypersonic in the similar way. How do we define the hypersonic actually? Definition of hypersonic has basically two dimensions. The first dimension is saying that hypersonic is not defined upon Mach number. So definitely it is associated with the speed, but there is no sharp boundary across which the flow becomes hypersonic. So we don't have any definition of Mach number, any use of Mach number in the definition of hypersonics. So how do we define the hypersonic? The hypersonic is defined based upon atmospheric phenomena. If you remember, in fact, here also this topic is showing here the hypersonic atmosphere. We never talk about subsonic atmosphere, supersonic atmosphere, because these atmospheric phenomena are directly linked with the Mach number, and Mach number has a very strong dependence, a strong influence on these atmospheric phenomena. Like if the Mach number is very low and the speed is slow, then it is subsonic regime. In subsonic regime, the viscosity is going to be predominating characteristic, and boundary layer will be the predominating kind of phenomena available. These are all very much depending upon the Mach number. But in the case of hypersonic, there is no fixed Mach number which is going to actually influence the hypersonic phenomena. So the hypersonic phenomena directly find their place in the definition, and wherever this phenomena are available, when we find these particular phenomena or specific phenomena are actually affecting and showing in the flow, we very conveniently call that regime to be the hypersonic regime, and there is no sharp boundary for that. There is no fixed Mach number for that. So in that case, hypersonic characteristics are thin shock layer. These are the hypersonic characteristics. Normally we'll just go in details also that these are the hypersonic characteristics which when they start showing in the flow and flow domain, we call that this regime is actually hypersonic flow regime. So first one is thin shock layer. I'll tell you what is it exactly, and then next one is entropy layer. Then we have viscous interaction, then high temperature flow, and finally low density flow. We know that hypersonic is not depending upon the Mach number. It's just now we saw that we define it actually based upon hypersonic phenomena. But exactly what Mach number can we call to be the hypersonic Mach number? Because finally it is the speed. even if this phenomena is taking place inside the atmosphere, we still have some Mach number which are actually affecting them. So what Mach number conveniently actually we can take to be the hypersonic Mach number? It's very clear here. You can see that the Mach number 3 to 5 shows the beginning of this hypersonic phenomena. We have just now discussed the 5 basic hypersonic phenomena which are actually available in the atmosphere, so we call it hypersonic regime. These hypersonic phenomena start showing up at the very beginning level as low as the Mach number 3 or 5 kind of thing, and they become fully grown, fully developed by Mach number 10 or 12. So if you want to say that there is a purely hypersonic flow regime, and everywhere we have all this phenomena available, then definitely we are talking about some Mach number which is beyond 10 or 12. Or if in between some Mach numbers are there, then this will be mixture of this kind of phenomena, and they will be dominating the flow regime or flow domain depending upon the Mach number. So hypersonic phenomena will be available, but they will not be fully developed in that cases. So conveniently we can say that these phenomena which start showing their existence at a Mach number as low as 3 to 5 and become fully developed by the Mach number 10 and 12. So when we have a Mach number beyond 10 or 12, we can say it's fully developed hypersonic flow. Thin shock layer. This is one of the characteristic of hypersonic flow regime. So let us see what it is actually. We can see one small wedge here, and then we have a sharp leading edge, and some supersonic flow is coming, some Mach number 2 is coming here, and then we get an oblique shock here. This oblique shock is attached here, attached oblique shock, because since it is not a blunt edge, it is having attached shock. Now flow after coming to this shock, it becomes parallel to the solid boundary and goes like this. It is very easy to understand and realize that in this region we have a wide open area available for the flow to take place, but after the shock we have a limited area available, so it affects its temperature as well as density. Now as the Mach number increases, here we have taken a example from Mach number 2 to Mach number 20 for the same deflection angle. The Mach number increases, the deflection, the angle, the wave angle, which is actually initially it is 53.5 degree, becomes very very low, and it's something like value is given 25 degree, and shock starts tilting towards the solid boundary, solid surface, and in this case this region becomes further thin, further very small. Actually the region and the region between the shock and the surface is called shock layer. We have a shock layer in which the flow takes place after the shock. So when the Mach number increases and goes in the very high region, something like what you call hypersonic region, then this region, the shock layer region, becomes very very thin, and in that case the density of the flow has to be very very high, because we have to have some we have to have a mass flow rate, and which is constant. So to maintain the continuity and the conservation of mass, we have to have a very high density flow in this particular region. This thin shock layer is basically a characteristic of the hypersonic flow. In this picture we can see the wave angle decreasing with the increasing Mach number. This is the theta beta m curve. Theta is actually your deflection angle, and then beta is your wave angle, and this for different Mach number the different curves are plotted. Take any particular Mach number, maybe the 10 degree of your deflection angle, 10 degree deflection angle. This region is talking about weak oblique shock, and this region is talking about a strong oblique shock. We know this already from the gas dynamics information, and this 90 degree where all the curves are matching is actually the normal shock solution, and this is corresponding to the deflection angle 0 degree, so there is no deflection across the normal shock. We know this already. And the other solution, for every shock, for every particular Mach number, we have two values. One 90 degree, the wave angle means 90 degree, is always fixed, that is normal shock solution, and The other solution for the same deflection, 0 degree deflection, we have one more solution for the same Mach number that is actually corresponding to the Mach number itself. So it starts from 90 degree and goes to the different values, and this is nothing but your Mach wave solution. So if you just find the Mach wave depending on the Mach number, if you find 1.3, 1.4, if you try to find the Mach angle, you will find these are the values actually. So extreme value is 90 degree, which gives the normal shock solution, and the other extreme is actually the Mach wave solution, which is still having 0 degree deflection, but the wave angle is not fixed at 90 degree. That it has different value depending upon the Mach number. The these are the oblique shock solutions. So the oblique shock solution, which is lying near this Mach wave, are actually the weak oblique shock solution, and these are the strong oblique shock solution. In the normal way, in the normal cases, we rarely see any strong oblique shock appearing in the supersonic flow, unless we are having very compressed air flow somewhere in the turbines and compressors. Otherwise, in normal cases, only the weak oblique shock appears. Now take this weak oblique shock phenomena. Let us see this Mach number is 10 degrees. Sorry, the deflection angle is 10 degrees. For the same deflection angle, when the Mach number goes from 2, this is 2, this 2 Mach number, so something like 40 degree. The wave angle is something like 40 degree. If it goes from 2 to 8, then this is the 8. Then deflection angle, for the same deflection angle, it has come to something like 18 degrees. So if the Mach number increases for the same deflection angle, the wave angle decreases from one extreme to other extreme, and in this case the shock layer becomes thinner and thinner. This is the characteristic of the hypersonic flow, and in this thin shock layer we also have very high density flow. Let us take another example of a hypersonic regime in which the Mach number is 36. A very high speed flow is taking place, and this region is very thin, very thin here. In this thin region we are having very thin shock layer. This thin shock layer, something like, you can say that these are realistic values for a Mach number 36. If you take the for a deflection angle of 15 degree, the wave angle will become 18 degrees. So hardly 3 degree recess is available for the flow to take place. So the shock layer becomes very thin in that case. Sometimes this thin shock layer doesn't only contain the air or the atmospheric air which is available. Sometimes it contains the chemically reacting flow, the chemically reacting medium. In that case, the temperature goes very high, because this chemically reacting medium, normally you can say that is also combustion also, because normally they react with the exothermic nature. So if in the exothermic nature the temperature goes further high, this high temperature further brings down the shock layer to a thinner level. So hypersonic regime basically faces a very thin shock layer, and that depends upon different Mach number, and this is one of the specific characteristic of the hypersonic regime. So when this start appearing, when they start showing the thin shock layer phenomena, we call that this is actually the hypersonic flow is taking place. When the thin shock layer becomes thin enough to be comparable with the thick boundary layer growing over the solid surface, the situation becomes a little bit complicated, because the thin shock layer starts interacting with the thick boundary layer, and this interaction is another specific phenomena which normally occurs in the case of hypersonic flow only, because shock layer becoming comparable with the boundary layer is possible only if the Mach number is very high and the wave angle is very low. This problem becomes important for the low Reynolds number. We know this we are aware with the Reynolds number actually. For the low Reynolds number, normally we assume and we technically take the flow to be a viscous flow. In the viscous flow, the boundary layer growth is very large. So for a large boundary layer growth, the thin shock layers become very comparable, and sometimes they even merge together. The thickness becomes almost same, and in that case the interaction becomes very severe, and then the analysis becomes very, very difficult because situation is complicated. And furthermore, we'll discuss in this what happens actually when the boundary, when the flow start comparing with the boundary layer. But this interaction is actually posing another challenge for the aerospace engineers to analyze and design the flow. Thin shock layer, when the Mach number, when the Reynolds number is high, low Reynolds number definitely very high. For low Reynolds number, we have a thick boundary layer, and that thick boundary layer interacts with the thin shock layer, and then it gives a interaction which complicates the situation. If the Reynolds number is very, very high, in that case, flow is essentially taken as a inviscid flow, and that in that case this thin shock layer becomes very advantage for us, because in that case the boundary layer will be very, very small, very, very thin, and then the interaction will not be much because this will not be comparable with the thin shock layer. So the thin shock layer itself becomes an advantage for the analysis purpose. The flow in the shock layer is practically inviscid, and thinness of the shock layer becomes a theoretical advantage, and a general analytical approach called thin shock layer becomes applicable. This thin shock layer theory becomes a very handy tool and is frequently used in the hypersonic aerodynamics for approximate calculation. Remind it, it's only approximate calculation, and this theory was postulated by the Isaac Newton in 1687. We shall study this when the time comes. Entropy layer. This is the another characteristic of hypersonic flow which I am going to discuss now. Let us take the help of the earlier picture again. We know that when a conical leading edge flows inside a in a supersonic flow regime, the shock remains attached with the body, and strength of the shock remains almost same throughout the length. In the case of hypersonic flow regime and the hypersonic vehicles, we normally have blunt nose. We normally keep a blunt nose because we want a separation here. So in the separation case, the strength of the shock doesn't actually remain same throughout the length. In the very near to the shock, near to this leading edge, the shock behaves almost like a normal shock. So the strongest region of the shock lies near the leading edge actually. Then gradually the strength of the shock keeps coming down from normal shock to a strong oblique shock, then to weak oblique shock, and finally the Mach wave downstream of the flow. We also know that across the shock, entropy change takes place because shock is a non-isentropic phenomena. Entropy change takes place, some losses take place there also. So this entropy change is also depending upon the strength of the shock. It's not like a particular shock will have the same entropy change throughout. So as the strength is varying from nose to the downstream, the entropy change will also vary according to that. So whatever the entropy change we see here, we may not have the same entropy change on the downstream on the surface, on the surface actually. So we normally get a variation in the entropy change as we go downstream. So now as the shock strength decreases downstream flow, a layer of entropy variation gets formed downstream of the shock, and it is called entropy layer. So this is, we have an entropy layer actually. This is also a very thin layer, and definitely it is actually inside the shock layer. This has to be inside anyway. This strong entropy layer flows downstream and wets the body for a large distance from nose. Now the boundary layer which grows near the surface, this is the boundary layer. This entropy layer is boundary layer. Now boundary layer which grows near the surface grows inside the entropy layer and is affected by it. So we have a shock layer here, and then inside we have entropy layer, and boundary layer which is remains in a very thin vicinity. We are assuming that this is a very high Reynolds number flow, so almost inviscid flow. So boundary layer growth is not very much. It is still within the shock layer, but now it is inside the entropy layer, and now it is becoming comparable here. Now when these two layers become comparable, they again start interacting and they start affecting each other. And we know that boundary layer is actually a viscous phenomena, so a lot of vortices are available inside the boundary layer, and entropy layer also contains a lot of vortices. It's also a vortex, a flow which contains a lot of vorticities, and this is actually according to the Korokos theorem from classical compressible flow. Now this interaction between the two regions is also called as vorticity interaction. So in the thin shock layer we saw that there is an interaction between the boundary layer and shock layer, and this gives rise to the very high density because of very thin shock layer, very thin region available for the same amount of fluid to flow. In the case of entropy layer phenomena, we are having some interaction with the boundary layer, and that gives rise to something called vorticity interaction. The presence of entropy layer causes analytical problem in the standard boundary layer calculation on the surface, because there is no certain idea now about what will be the proper condition, at the outer edge of the boundary layer. What is the normal condition at here? We assume that in this region the flow properties change, especially the velocity, but at this region whatever the flow properties available in the free stream, the same flow properties will be available here. So we are sure now that at the end of the boundary layer or boundary layer edge, or something like at the boundary layer thickness, this is thickness is there, at this edge we have the similar property what is available in the free stream flow. But when this entropy layer starts interacting with the boundary layer, this is no longer the same, and we are not exactly sure what is this. We are not sure that what is the new value, because this entropy layer has changed these values and this phenomena, this situation, and what is the new values, that we are not sure. So that gives another challenge in analysis of the hypersonic flows. This tells the vorticity interaction, which is caused by the interaction of the entropy layer, which is thin, very very thin, because of thinness of the shock layer, and when it becomes comparable with the boundary layer, they start interacting, and since both are housing the vortices, this interaction is termed as vorticity interaction. Students should remember this. The third one is viscous interaction. So now let us discuss this. What is it actually? This is a typical situation when the boundary layer is formed on the any solid body when it is moving in the air or any fluid. So in this boundary layer we can see that there is a variation in the velocity because of the viscosity, and the no slip condition has to be fulfilled. The fluid velocity in the layer adjacent to the solid surface has to actually become 0, because there cannot be any slip condition. So the fluid velocity is 0, so the total fluid particle comes to rest, and the high speed which particle moving in the free velocity regime and the free stream flow, who contain very high kinetic energy, that kinetic energy is actually converted into the internal energy, because the fluid has to come to rest. So that internal energy is converted here, and that is directly affecting the temperature of the fluid in this particular region, actually here. So this picture shows that in the fluid, in the boundary layer, the variation of the flow that takes place in the flow velocity, it goes from the zero at the surface to the free stream velocity as per the normal definition. Definitely we just now discussed that these interactions of the boundary layer the other thin layer, thin shock layer, and the entropy layer also affects the velocity. But in normal case, the velocity at the outer edge of the boundary layer is the velocity of the free stream flow. So by keeping those two earlier discussion aside, we're just trying to discuss what happens in the case of boundary layer, which is actually a viscous phenomena. In this viscous flow, the velocity varies from 0 to the maximum velocity here. So this is the 0 level, and this is exactly 0. So this is the 0 level at the 0 distance from the surface and the 0 velocity. It will start varying. So this is your completely that the velocity ratio, and this goes to a maximum equal to 1, where at the outer edge the velocity becomes equal to the free stream velocity or inflow velocity. So in this region you can see that there is a huge dissipation. Here it's almost 1. The boundary layer growth is boundary layer thickness is somewhat like this, and this is the region where there is almost becoming 1. This region, there is a huge slowing down of the fluid takes place. This slowing down takes the viscous interaction, viscous dissipation, and that viscous dissipation makes the kinetic energy to be converted into internal energy. That internal energy converts into temperature. So if you just plot the temperature in this region, how it looks like. Here the temperature of the surface, this temperature at the 0 level, the T by T wall is equal to 1. So the fluid exactly at the level of the adjacent to the surface is actually having the temperature of the wall itself. There is no discontinuity. Now as the distance go away from the solid wall, the temperature start varying, and at the final level, when there is boundary layer, beyond the boundary layer, again temperature ratio becomes equal to 1, confirming that the temperature of the surface is actually equal to the temperature of the free stream flow. But in between, because of the viscous dissipation, when the huge amount of kinetic energy is actually dissipated into the heat, the temperature varies. Temperature goes very, very high just near the solid surface inside the boundary layer. It's not beyond the boundary, inside the boundary layer. This becomes very high. So in the case of velocity boundary layer, when the velocity variation is, you can see this is the we are having somewhat similar normally in normal kind of variation in the velocity, which normally we encounter in any kind of flow, which is subsonic or supersonic. But in the case of temperature variation, we have a very peculiar kind of variation here. Students should not be confused here that this is actually a temperature boundary layer, thermal boundary layer. No, it's not thermal boundary layer. This is still the velocity boundary layer, but we are now trying to see the variation of the temperature inside this velocity boundary layer, and this is having a very peculiar behavior. And this region is because of actually the viscous dissipation, and a lot of huge kinetic energy is dissipated in the form of internal energy, which causes the temperature to go high. Now this high temperature affects the viscosity. You know very well that the fluid viscosity is affected greatly by the temperature, and for the liquid the viscosity comes down, and for the gases the viscosity goes high with the high temperature. So a high temperature will actually cause a high viscosity there. This high viscosity will further cause the viscous dissipation. So a further increase in temperature. Is it perpetual? They start giving a positive feedback to each other. So a very high temperature is actually anticipated in this particular region. Now let us consider this boundary layer again. Here we have taken this small section and enlarged it, so you have a velocity variation here. In this particular region, we have already discussed that the pressure variation perpendicular to the surface remains constant. We have seen that the pressure only varies. If you want, I think you should guys should recall the learning. We learned something about this pressure variation in the boundary layer under the subject of heat transfer. You study the boundary layer and heat transfer in the convection boundary layer, or something like forced boundary layer, forced convection in a fluid flow. There we studied and we saw that the pressure variation remains same. So in this region the pressure will remain same. There is no variation in pressure. Pressure is varying only in this direction, from in the x direction. In the y direction, perpendicular to the surface, the pressure is not varying. We have discussed this already. In the pressure is not varying, then what happens is temperature is varying. Temperature goes high, pressure remains same. So, but natural density has to come down at this level. If temperature goes high, density comes down. So, in the boundary layer, actually, in the boundary layer, density comes down. In the shock layer, density goes high. The reason was we have to have some kind of high density to compensate the flow and the fluid flow and maintain the continuity equation, the conservation of mass. But in this region, if you look into the microscopic level of the boundary layer, the density comes down because temperature is very, very high. So we get a very thin flow flowing here. Now, a very thin density will try to compensate the mass flow rate by increasing the boundary layer thickness. That's very evident, because again we have to have sufficient amount of mass flow rate to maintain the continuity. And a large temperature will actually cause the viscosity to go high, which in turn will make a very viscous flow. That viscous flow will actually make the boundary layer to grow faster. So both of these reasons, both of these conditions jointly actually affect the boundary layer to grow large. And then this boundary layer relation, boundary layer thickness is also depending upon the Mach number. So the Mach number increases, boundary layer thickness increases too, and it increases according to the square curve. It's here, you can see that it's m infinity square, and then we have this square root of the Reynolds number. So it will become large in the hypersonic regime, and the reason is that explained above. This equation is affecting for the boundary layer to grow and become very, very large. So we have a very thick boundary layer in the hypersonic regime depending upon this Mach number. This thick boundary layer in hypersonic flow can exert a major displacement effect on the outer inviscid flow region, and this will cause the body to appear much thicker than it actually is. It's very much evident to know. Now, due to the extreme thickness of the boundary layer flow, outer inviscid flow is greatly changed, and the change in the inviscid flow in turn feedback to to affect the growth of the boundary layer. So boundary layer is further growing. This is just perpetual. They adjust themselves, but keep giving positive feedback, and they keep growing. The major interaction between the outer inviscid flow and the boundary layer is called actually the viscous interaction, which takes place in a loop. The viscous interaction can have important effect on surface layer pressure distribution. Hence, the lift, drag and stability of the hypersonic vehicle, even the skin friction drag, the heat transfer, all are affected. It's not just they are just interacting and they post to the analysis problem. They affect everything. So whatever the analysis people have done depending upon the high speed flow in the supersonic regime, that is completely ruptured because of this viscous interaction. So it's not just we change the Mach number. You change the Mach number, and this Mach number will give you the values of the velocity and of the flow parameters depending upon the Mach number relation. It's not like that. Some new interactions like viscous interaction is coming, and this viscous interaction will actually affect almost everything. As a matter of fact, it affects the entire performance of the vehicle, and then we have to consider everything. This picture illustrates the effect of viscous interaction on the pressure variation on the surface of sharp right circular cone. This is sharp right circular cone, and very sharp leading edge is there, a spike like a structure, and then shock will be generated. Definitely here it will be attached shock. So because of the strong growth in the boundary layer, which start interacting with the inviscid flow beyond the boundary layer, they affect the pressure variation on the surface, and this is very clear. This is your normal pressure variation. This is the pressure of expected, and this is because of the this is the pressure. The PC is the pressure expected with the simple experience, and P is the pressure actually existing because the existence of the thick boundary layer and the viscous interaction. This viscous interaction gives a very high pressure actually available at the leading edge, and this effect of the viscous interaction keeps coming down, and far downstream is actually becomes equal to the pressure becomes equal to the constant pressure throughout. It is clear that the effect of viscous interaction is greater near the nose area. You see that nose area is greater, and its effect diminishes further downstream, and far downstream it approaches the value equal to the inviscid flow value. If this line goes far downstream, it will become equal to 1. This is what is supposed to be as per the non-viscous interacting fluid. The viscous interaction affects even the pressure variation. We have seen this thing. The high temperature flow, this is also one of the special characteristic of the hypersonic Mach number. We already have discussed about the high temperature generation within the boundary layer in a hypersonic flow due to the viscous dissipation. We saw that because of the viscous dissipation, the kinetic energy is converted into the internal energy, which actually gives rise to the high temperature. This high temperature is not just a simple high temperature. This actually becomes so high sometimes that it can even cause the dissociation of the fluid, flowing fluid, or sometimes it can cause the ionization. So the gas which is flowing with this particular speed can become so hot inside the boundary layer that it can even ionize. So if the surface of the hypersonic vehicle is protected with the ablation material, we know that one of the method to cool down the surface and protect the structure is the ablation heat transfer, in which the volatile material is actually painted above the surface, which start evaporating at high temperature. So when this ablation happens in the boundary layer, not only the ionized molecule or gases will be available, even the hydrocarbon, complex hydrocarbon, which are the product of ablation, they also are available. So whether it is a dissociation or ionization or the hydrocarbon chemical reaction, on both the accounts, the surface of the vehicle will be actually wetted by a chemically reacting boundary layer. So we will have in this particular region, if the flow is taking place at the hypersonic value, Mach number is in the hypersonic range, the boundary layer will be containing a chemically reacting phenomena because of ionization, because high temperature, plus some ablation material which can actually the hydrocarbon, they start reacting. So we have a boundary layer which is actually chemically reacting. So in this case, the boundary layer has to be actually accounted and estimated for the chemical equilibrium also. The chemical equilibrium has to be accounted while doing the estimation. This happens so because for the hypersonic flow, not only the boundary layer will be chemically reacting, there is the entire shock layer too can be dominated. So suppose the Mach number is not very large, then this thing will still be there. The boundary layer still will have this problem, or I can say this phenomena. It's not a problem, so we can analyze it. But the other region can be actually ignored, and we can do the analysis. We can actually find the flow behavior. But the problem is when the Mach number is very, very large, the wave angle is very small, and we have a very thin shock layer, which we have discussed already. In this shock layer, when it starts comparing itself with the boundary layer. So the entire shock layer is ionized flow and actually a chemical reacting flow. So in that case, the chemical equilibrium or chemical kinetic analysis becomes important. So we have to have that also, because not only the boundary layer, that the entire shock layer is actually dominated by the chemical reacting flows. So this is the case of boundary layer where we have high temperature. But this is not the only region where we get the high temperature, and this is not the only reason also. In the boundary layer we get high temperature because of viscous interaction. A kinetic energy is converted into the internal energy. But in the case of a hypersonic vehicle, normally we try to keep a separated flow. We try to separate the flow, detach the shock here in this region. And in this region, where very near to the nose, the shock behaves actually like a normal shock, and the Mach number is very, very high compared to something 36. Then in this region, after the shock, we can get a very high temperature, somewhat near to 11,000 Kelvin. We can understand this temperature is so high that in the case of combustion, by combusting the fuel in the combustion chamber, we normally get temperature something like equal to 2500 to 2800 Kelvin. Now without any combustion, just because of high velocity and generation of a shock, which is actually of the nature of normal shock here, we get a temperature of something like 11,000 Kelvin. This high temperature is again very much capable of ionizing the fluid in this region. So this is strong normal shock at very high Mach number can generate very high temperature within the shock. This very high temperature sometimes can be good enough to cause the molecular dissociation of the glowing gas. This gives rise to the complex situation that at these elevated temperature, the concept of calorically perfect gas doesn't remain valid. That's the problem. And assumption of constant thermodynamic properties gives unrealistic estimation. So at this temperature, when we don't have a constant properties, especially this specific heat capacities Cp and Cv, if they are not constant, then gamma is not constant, and if gamma is not constant, then whatever we estimate for the temperature and other things, depending upon the constant values, gives very unrealistic values. You'll see that how unrealistic they are from the existing values. Hence, it becomes essential to take into account the temperature dependence of specific heats and their ratio as function of temperature for rational estimates. Now we are not taking this specific heat capacities as constant. We have to actually take as temperature dependent parameters, and we inject the temperature in the formula of Cp and Cv, and then you use them. So complexity increased further. This picture gives some idea about this flight of Apollo's re-entry at Mach 36. This is Mach 36. This Apollo's re-entry is there. This also you can say that if the vehicle flies with a very high speed, I hope you remember this, the maximum re-entry of the Mach number for the space shuttle is something like 25 Mach. This is a frequent flight kind of mission, and Apollo was having just one time mission. So in this also the Mach number is large enough to create a very high temperature. So inside the high temperature we are having ionized or plasma kind of flow, and this is wetting the throughout. It's not any particular region. It's not only in the region where we are having the boundary layer. Inside the shock throughout, normally we see very high temperature gases. So we are actually, the entire body of the vehicle is wetted by the plasma type of flow, and this gives rise to the varying specific heat capacities, and that assuming them to be constant gives a very unrealistic value. We'll see them just now. Now Cp and Cv are not constant, hence it becomes essential to take into account the temperature dependence of a specific heat and their ratio as function of temperature for rational estimates. We can see that here if you assume the Cp and Cv to be constant, we'll get this kind of curve. So we have a calorically perfect gas situation here, but this is unrealistic. What actually we normally get in the case of variable Cp and Cv and gamma is this curve. High, very huge difference is there actually. You can see there. These are the normal IRBM, normal Mach number 6, ICBM something like more than 7. Then we have orbital, some Mercury and Gemini space shuttles. They go for Mach number 8 during re-entry, and this then you go for higher and higher. So mass return is also there. So in this case, the temperature will be very high if you calculate based upon calorically perfect gases, but actually by considering the chemical equilibrium and chemical reacting gases, we get this kind of temperature. So it becomes important, and this difference is so huge that we cannot actually ignore the variation of the specific heat capacities with respect to temperature. Now, the dependence of thermodynamic properties on temperature mainly comes from the microscopic changes in the fluid due to the increase in internal energy. You have seen this internal energy. That internal energy increases because of dissipation of the kinetic energy, which is lost actually. Now, this increased internal energy leads to the vibration excitation followed by the dissociation and finally ionization. So we have we just molecules start getting apart. We just get them ionized because of high temperature available there. The extent of increased internal energy, this causes the specific heat capacity to become the function of temperature. So the ratio of specific heat gamma also becomes a function of temperature. For the air effect becomes important. This becomes above a temperature of 800 Kelvin. If the temperature of air becomes more than 800, this variation in Cp and Cv becomes more important, and we must account them. Let us have a small idea how it actually happens. This simple situation is showing that how these two molecules of the gases are joined together. A spring-like bond is given actually, but they are actually they remain together because of the interaction of the electrostatic or the intramolecular forces. They remain together. When they start getting more and more energy in the form of thermal energy, the temperature start rising. So these molecules start getting apart. They start getting excited, and this excitation happens almost at 800 Kelvin. They start getting excited, they start shifting away from each other, and that they can say that now air is going towards ionization. Now it has not ionized yet, and at very high level they start vibrating also, and then finally they just move apart and become ionized. If you look into the air configuration, mostly it is actually composed of oxygen and nitrogen. So in oxygen actually starts showing some ionization, and their molecules start dissociating from each other as a temperature of something like 2000 Kelvin, and at the 4000 Kelvin they become fully dissociated, and every oxygen molecule available will be in a dissociated form. Nitrogen starts dissociating at 4000 Kelvin, and by the time of 9000 Kelvin nitrogen also becomes fully dissociated. So if any vehicle is having a temperature of the surface something like more than 9000, and we know that we have already seen that a vehicle flying with the 36 Mach number will get an temperature of something 11,000 Kelvin. In that case, almost the whole surface will be actually engulfed by the ionized or something like chemically reacting plasma type of environment around it actually. So the vehicle will be flying like it is flying inside a plasma, not inside a fluid. Rather it's a plasma ionized state is going like this. In this situation, the treatment of air or any fluid flowing with the hypersonic speed over any configuration should be done properly by incorporating all the microscopic changes, because these changes are actually taking place at the microscopic level. It's not just a simple temperature. The temperature is actually rising or changing depending upon the changes taking place at the microscopic level, at the molecular level. So this has to be accounted, and changes in the thermodynamic properties should also be actually accounted and should be done properly, and then the dependence of these properties on the temperature should be done very carefully. And this dependence is actually a non-linear dependence. It's not change, it doesn't change linearly. Hence, analysis or prediction of flow field become very difficult. If we have it linear, we can actually have some kind of soothing effect. We can actually analyze it. We can have some prediction based upon the previous cases, but this is highly non-linear. So we just have to have some two kind of situation here. So the two assumptions we normally make here, depending upon the fluid velocity at the molecular level, at their molecular molecular vibration and excitation, and their mainstream flow. Depending upon their relative motion, we normally have two types of concepts which are going on in the case of flow. So we have assumption. We make two assumptions. See, the microscopic changes or reactions are at faster rate than the movement of the fluid. Then it is treated as equilibrium flow. It's in equilibrium because it's very fast. Otherwise, it is treated as non-equilibrium flow, which is difficult to analyze. All these difficulties are collectively termed as high temperature effect, and also frequently referred to as real gas effect. Although some technical reason we don't like to call it real gas effect, because it's realness, everything is real, but it's a high temperature which is causing all these things to happen. If the microscopic changes or reactions take place at a faster rate than the movement of the fluid, then it is called equilibrium flow. Otherwise, it is treated as non-equilibrium flow, because these two movements are comparable to each other, so they both start affecting. So they are not in equilibrium, and that is difficult to analyze. We have seen already. Now there are some consequences of the presence of high temperature reacting fluid or plasma in the vicinity of the flight vehicle. They are something like influence on aerodynamic parameters, aerodynamic heating, and communication blockout. Flight parameters like pitch, roll, drag, and deflection of control surfaces, they also they normally get affected, and this deflection get deviated heavily, and give now some unusual estimates are coming because of calorically perfect gas, which are not available because of the high temperature. So presence of a hot fluid near the cold vehicle surface induces high temperature also, not only through convection but also through radiation. And communication waves, which are necessarily something like radio waves, get absorbed by the free electrons, and these free electrons are formed by the ionization of the atmosphere, and this phenomenon is called communication blackout, where on board and ground communication gets terminated. So a communication problem also comes because of this ionized fluid available around the vehicle, because they absorb the radio waves. Low density flow. So low density flow, this is the last characteristic we are going to discuss today, which is also a property of the hypersonic flow. In a normal situation, normal scenario, the air contains a lot of particles, millions of particles in a very small space, and these particles are always in random motion, and they travel with a very fast speed in all the directions, whichever direction actually they normally travel in the straight direction, and because of a lot of other particles are available in the vicinity, they just got collided. When they get collide, their direction get changed, so they start traveling with other direction, and they keep colliding each other, and they keep actually rotating, and they keep actually colliding and changing the directions. These collisions are basically 100% elastic, so there is no loss of energy. Now these molecules, when they travel and when they collide, the distance they travel between the two collision is not always the same. Like suppose it collided here, and from this collision to the next collision it has this much distance, and in the next collision it may travel a little longer, and then next collision it may travel a little shorter distance. So these distances which actually they are traveling between the collisions are not always the same, but on the average they travel some distance between any two collisions, and that distance is called actually the mean free path, and this is denoted by denoted by lambda actually. So by definition, the mean free path is the distance molecule of a gas travel on the average between any two collision, and at the standard sea level condition, this lambda, the mean free path, has a value of 6.63 into 10 to the power minus 6 meters. It's practically a very small distance actually, and this small distance implies that when someone moves at a sea level condition, the number of impact of the air particles on his body will be so large and continuous that individual impact of the particles will be hardly felt on the body. So it looks like the molecules are continuously impacting on the body, and they're almost everywhere available. So it doesn't give any effect or any feel, and looks like the individual effect of the molecule is actually missing there. Throughout the body, the effect is so continuous that throughout the body this impact is felt, and it looks like a continuous medium. So this will feel like a continuous medium, and the flow of medium too can be treated as continuous, and this concept of accepting the flow to be continuous in a airflow in the technology is called continuum. Fluid is everywhere. So wherever you move the hand or go and just walk or do something, every movement is actually impacted by millions of particles in a very small space. So their individual effect is actually just become immaterial, or also it's actually not very possible to sense them. So it become actually not possible to find. And in this case, this concept that everywhere is available is called as a continuum. The most aerodynamic problems are dealt with the assumption, and this concept of continuum is very much valid. And all the theories and the equations which are derived related to the motion of the fluid are actually having this assumption that the fluid is continuum and the medium is continuum, and they have the similar impact throughout, and it is individual impact is not very important, it's not accounted, it's not actually possible also, because millions of particles are actually impacting. Now as we move at the very high level, a higher altitude, the possibility of the existence of large number of particles in a small space, a very small space, keep diminishing, and particles keep getting apart from each other. So now in a space we have a smaller number of particles available, and this depends upon the distance, the altitude of the location from the surface of Earth. So higher and higher altitude, if we keep going, we'll get actually the lower of the lower the number of particle available. At altitude about 105 kilometer, 105 kilometer, the mean free path of the air particle becomes as high as equal to 1 feet. We started about 6.63 into the power minus 8 meters, minus 8 meters, right? Minus 6 meters. And then it becomes comparable, something like equal to 1 feet. So within 1 feet, if a body of something like lesser than 1 feet is moving in the air, there are very much chances that there will not be any impact of any molecule in the air, or maybe it will impact just by one molecule, because other two molecules are at the span of 2 feet. So an individual effect is felt there, and that individual effect actually accounted, and this account cannot be done by the continuum assumption. So we just go for the kinetic theory. Well, in this widely spaced particles of matter, under these conditions, the aerodynamic concepts, equations, and results based upon the assumption of continuum begin to break down, and they are no longer valid, and they don't give the realistic values. They just give very, very ideal values which are no longer applicable. So we start changing our point of view, and we start using the concept from the kinetic theory to actually analyze and find the these aerodynamic behavior of the fluid. And this regime of aerodynamics is actually called low density flow. Now the implication and the immediate consequence of this low density flow is that the most favorite and the most vital concept we have been seeing till now, that the no slip condition is no longer valid. So on the wall now we don't get a zero velocity, so the fluid starts slipping there, so we have some kind of extra velocity available here. This is the pipe flow, or the flow between the between two plates. You can see that in the normal cases we have, when we have a continuum concept, we have this kind of flow velocity, a flow velocity profile inside the fluid. And now if it is actually flowing with the hypersonic, if the particle measure is available and continuum assumption is broken, and mean free path is large enough, then we normally get some non-zero value velocity available at the surface of the wall. And this asked to analyze this in a different way. So this situation is called the velocity slip condition. And in the analogous fashion, the gas temperature on the surface, which is normally the temperature of the surface itself, now becomes something different. So this slip condition is not only actually occurring in the case of velocity profile, this starts affecting even the temperature profile also. Unfortunately, I don't have that picture. So temperature also, which is supposed to be the temperature of the wall, actually you start getting a small jump there. So what we normally call the temperature jump condition, the temperature no jump condition. So there is no jump available. In this case, the jump is available. So we call also the slip condition. So that we have temperature slip condition also available because of the continuum assumption being failing, and then the mean free path becoming large enough. So on the onset of these slip effect, the governing equation will assume the still can be actually assumed with the continuum effect. So whatever the equation we have derived based upon this continuum condition can still be used despite this condition. There no slip conditions are available in the velocity as well as the temperature. We can still use the continuum cases and continuum continuum equations which you have derived, but in this we have to inject a condition of no slip velocity and no slip temperature also. So on the boundary, when we put the condition on those equations, at the time we don't have to put v is equal to 0 here or t is equal to ts, the surface temperature. We have to put proper value. So jump, if the jump is accounted, even the equations which are derived assuming continuum concept can still be utilized. However, if the altitude keeps increasing, then there comes a certain point where the equation, the velocity, the particle, the mean free path becomes so large, and the particle continuum assumption is not at all valid, and situation becomes so typical that even the continuum equations are no longer valid anymore, even by applying the boundary conditions. So at that time, the kinetic theory must be used to predict the aerodynamic behavior of the flow. So finally, the air density can become so low that only a few molecules impact on the surface per unit time, and after the reflection, they never collide with the incoming molecule. Such regime is called free molecule flow. So now let us just see that what happens when we start entering from the very high altitude. So that high altitude where the mean free path is very large, and the chances of having a lot of collision with the air molecule and the surface is very, very low. At that time, we are having a regime we call the free molecule flow or free molecule regime. In that regime, it is very much important to actually use the kinetic theory, and the continuum and the equations developed on the continuum assumption is no longer valid, no matter whether we put the conditions or not. Such regime normally begin at the age of at the altitude of 150 kilometer. So during re-entry, the space shuttle faces a flight from the much rarefied atmosphere to denser atmosphere. So this will shift from free molecule regime to a transition regime. In the transition regime, the individual molecule impact will be there. In the free regime, the individual molecule impact are felt, and they are accounted by using this kinetic theory. And in the transition regime, where no slip condition becomes important, so we can still use the continuum equation, but the no slip condition has to be accounted actually. And then we go for the further coming down, we get the continuum regime, in which the continuum of the flow becomes more important, and we can easily use and those equations which we have derived, and they remain valid actually. One thing to be marked here is that we when we discuss the low density flow or the low density region, and some kind of equations valid for this region or not, we are not actually talking about the velocity. So we are basically talking about the situation. Again, this is atmospheric situation, which is affected by basically the physically affected by the altitude from the Earth's surface, and technologically affected by similarity, one similarity parameter which we'll discuss just now. So in this region we normally don't talk about the Mach number, and then in fact even a particle traveling with a subsonic and supersonic speed will also have this phenomena applicable to it if it is traveling in the in that particular regime where the density is very, very low. The similarity parameter, which actually defines and determines this flow, that low density flow, is actually Knudsen number. And Knudsen number is defined by lambda by LC, and lambda is just now we have defined lambda is actually the mean free path, and LC is the characteristic length. And characteristic length also depends from case to case. We know already that in the case of pipe flow, the characteristic length is taken as the diameter, while in the case of flow over a flat plate, we take the distance from the leading edge as the characteristic length. So this Knudsen number determines whether the low density regime is applicable or not. The applicability of the flow regime and their respective governing equation, which is controlled by the Knudsen number, is shown in the picture below. This is the picture actually. So this picture shows that what is the equation which will be applicable depending upon the Knudsen number. This Knudsen number, if very low, and lambda is very low, so in that case continuum model is very much applicable, and then we go for continuum equation. There is nothing wrong in that, applicable, and we don't have to actually track a single molecule, because the fluid we have like a continuum, and it's continuous, and the individual effect will be missing there. Now at the Knudsen number start increasing, then we have some that Euler equation start actually applicable, and this equation is applicable till actually the Knudsen number equal to 0.1 to something like 0.3, like that, and beyond that it is not it's not very applicable. We have to use some different equation. From the picture it is clear that for the Knudsen number less than 0.2, the continuum concept is very much valid, and the continuum Navier-Stokes equations are very much applicable there. However, the slip conditions start taking place as low as for the Knudsen number as low as 0.3. So it is something like very it's interesting, isn't it, that in the case of compressibility also we saw that the Mach number something like even if the flow is subsonic, if the Mach number is 0.3, the flow becomes compressible. Here also something like, even if the continuum equations, Navier-Stokes equations are applicable, the conditions of the no slip conditions has to be injected and actually put there to do the correct analysis, and that becomes important for the Knudsen number as low as 0.03, something similar. Even figures are similar. So for the large value of Knudsen number, slip conditions start taking place, and this must be accounted for any regime for more than Knudsen number 0.03. And the free molecule flow becomes effective the moment the mean free path becomes comparable to the characteristic length. So at that time something like Knudsen number will start approaching equal to 1, and that time the slip conditions are become very important, and that time looks like the Navier-Stokes equation start failing, and then the range for the applicability of the free molecule regime extends to infinity, and after that to the infinity. From there we can call actually the free molecule regime. So we have a continuum regime here from here to here, and it's not exactly Knudsen number equal to 1, but it's very near to 1 actually. So we can take actually somewhat similar to 1. We can use actually continuum model. But the moment it goes beyond 1, we actually we enter into the no slip condition regime, which is actually opposite to the continuum regime, something like subsonic and supersonic, what we see actually. And then this no slip condition actually not valid, and the slip condition regime is applicable there. That is applicable throughout up to the infinity. So the transition regime now is lying between actually within the range of Knudsen number equal to 0.03 to 1. So between 0.03 to 1, the Navier-Stokes equations are still valid, like the flow is subsonic, we can say, but becomes compressible. So the Navier-Stokes equations are still valid, but since the Knudsen number is more than 0.03, the no slip condition is not valid, so the slip conditions are actually implemented. So as I just now told that this is actually not depending upon the Mach number. In fact, Mach number is not playing any role here. It all depends upon the Knudsen number, which is the similarity parameter, which determines whether the equation will be the regime will be actually the free molecule regime or the continuum regime. That will be totally determined by the Knudsen number. So this Knudsen number also depends upon two parameters: the that mean free path and the characteristic length. So sometimes if the vehicle has very large characteristic length, and then even in the mean free path is large enough, if we as overall the Knudsen number becomes lower, we can still use it Navier-Stokes equation, and we can say that it's a continuum model. The continuum model is very much applicable even there. But for some cases, it may happen that even at the lower altitude, not very high altitude, where where the mean free path is not very large, but the characteristic length is very small, then the continuum model starts failing. So we have to go for the kinetic equations there. So this is totally depending upon this mean free path and the relative characteristic length. Mach number doesn't play any role here. On concluding the low density up to the altitude of 90 km from the Earth's surface, where Knudsen number remains below 0.2, the applicability of the continuum assumption remains intact. We can very well use this thing even without the application of the no slip condition, the slip condition. However, the application of slip condition and no temperature jump condition becomes applicable at the as the value as low as 0.03. Above this altitude, at up to 150 km from the surface of Earth, density becomes very low, and assumption of no slip condition start losing its validity. So the transition range lies within from 0.02 to 1, and where continuum assumption can be applied with no slip condition correction. Beyond this altitude of 150 km, density of the atmosphere becomes so low that a need for change in governing equation arise in this regime. Hence, kinetic theory of gases finds its application for hypersonic flight at such altitude. In fact, a discrete particle model, which actually gives you the kinetic theory, actually utilizes the kinetic theory of the gases, is applicable everywhere. Unfortunately, it will be difficult to track a single particle in the continuum range, when it's actually the fluid is taken as continuum, because millions of particles are available. So in that case, despite this Boltzmann equations, all these things are applicable, that discrete particle model is applicable, we go for continuum model, because there are millions of particles are available in a very small space. But as they become very rare, and we start losing this the implication of application of this continuum model, we switch to a discrete particle model, where the kinetic theory of gases takes the importance, and then we just analyze this. This is the total summarization for the discrete free molecule, or that low density flow of the hypersonic regime. Another little information about here is that suppose the flow is taking place on the flat plate. So we know that the characteristic length of the flat plate is actually not a fixed one, and it is the distance from the leading edge which actually affects the characteristic flow. So characteristic flow, if it is actually if you analyze the flow on a flat plate in the hypersonic regime, the Knudsen number will actually it will be very large in the beginning, because because near the nose region the characteristic length is almost near to 0, so the Knudsen number will be very high, no matter how small the mean free path is. So this region becomes very difficult to analyze, and normally we don't, this region also doesn't extend much, so we normally ignore this region actually. But even if the characteristic length is that mean free path is large, the characteristic length keeps increasing with the location from the leading edge. So at particular location this becomes actually smaller, so the continuum concept start applicable there. So in the case of a flow over a flat plate, the continuum model is applicable downstream when the characteristic length is large enough to make the Knudsen number small. But in the case of near the nose area or leading edge region, this actually the discrete model is more important, which it should be applied, and the continuum model fails there, and the Navier-Stokes equations are not very applicable. Recapitulation. So let us just summarize quickly what we learnt today in this entire video lecture. We know that we actually define the hypersonic regime, and hypersonic regime is not the hypersonic velocity, but the hypersonic atmosphere, because all the characteristics which are being utilized in defining the hypersonic regime are basically the atmospheric properties, not the velocity or the vehicle property. So the hypersonic phenomena are that thin shock layer and the entropy layer, and then we have viscous interaction, and then we have high temperature flow, and finally the low density flow. Low density flow is not actually related with the density, but more the velocity or the Mach number, but most of the hypersonic regime are actually lying in the very high altitude where density also very low. So this low density flow is also accompanied and associated and studied together with all these four other phenomena. They all are actually joined together called hypersonic phenomena. This picture summarizes the entire thing together. We have very thin shock layer. The thin shock layer is there because of high density flow, high velocity flow. The shock layer is actually very thin, and shock is very close to the surface. And then we have some entropy layer, because there is a change in entropy as the length changes, as the strength changes of strength of the shock changes. So we have a entropy gradient that gives rise to the entropy layer. Then we have high temperature also available inside it, and this high temperature also available because of this in this region, because of very high temperature generated because of strength of the shock that is somewhat treats as the normal shock, and some other region high temperature available because of the thermal dissipation or viscous dissipation inside the boundary layer. And then we have this viscous interaction here. In the case of entropy layer, we normally see the vorticity interaction, and here we have viscous interaction. And this boundary layer growth is actually directly proportional to the m square by under root re, the Reynolds number. And then finally, at the high altitude, we also face the low temperature, low density flows, and then in that case, all these 5 hypersonic phenomena are summarized in just one picture. Now at this level, I can ask one question, that we discuss this hypersonic phenomena. We call them hypersonic phenomena because they exist in the hypersonic region. Do they actually exist only in the hypersonic velocity or hypersonic flow, and are completely absent in the case of low speed flow, maybe supersonic or subsonic flow? As a matter of fact, these are the similar concept or similar implications are there. Like in the case of we see subsonic flow and supersonic flow. In the subsonic flow, we have compressibility almost ignored, and viscosity is very important. In the supersonic region, normally we ignore the viscosity and believe that flow is compressible, and compression phenomena, the shock appearance are very much important there. but actually these phenomena, both compressibility as well as viscosity, are always available depending upon their relative that importance and the relative strength which start affecting the flow parameter. We normally account them, and we also call them flow to be compressible or the viscous flow. Something similar happens here also. These phenomena are always available. When you say that thin shock phenomena, thin shock layer, what does thin shock mean? Thin shock doesn't mean the word thin itself is very relative. This is available everywhere, but this, in the case of hypersonic regime, the thin shock layer becomes so thin that it start interacting with the boundary layer, and then it becomes very important to treat it as in a different manner. It's not simply, it's not just simple, and you just can't actually treat it like a general flow. So this phenomena only becomes important in the case of hypersonic regime. Otherwise, they are available everywhere all the time. So with this word, we normally we just stop our class today, and I hope the students are enjoying these video lectures, and definitely we are now going to become more and more technical. I'll actually encourage the students to look more into the this hypersonic technology from the internet and from the books, and they can discuss in the classes, because in the class we'll have more time to discuss, because the main stream of the classes, the main information is actually delivered out of the class. So we call it the flip class kind of thing. So main information is delivered out of the class, and the ideas are conceived and assimilated inside the class. That's what is going to happen now. In the next class onward, we'll try to go into the equation mode, and they see the become more and more technical side. I think, and then but it'll be better if the students study and look into the various websites also, and try to gather more information about the hypersonics, and then we'll enjoy the class more. So see you in the next class. Thank you very much.